We could.
Once you do it, where you guys
We are live recording. We're not live streaming, but it's going to be posted afterward. Video. Yeah. We're streaming internally within GoDaddy. I guess there's 2,700 people or something. Oh, that's just on Slack. Yeah, so they have multiple people. Yeah, multiple accounts per person on Slack. Yeah, we got people here from Dubai / Spain. You're from Spain? From Barcelona, right on. I was just there. It's so weird saying it the way that people say it, here, because people don't think. If I say Barcelona, they think I'm silly, but that's how you say it. Thanks for coming. Specifically for this. Just a quick 22-hour flight or whatever it is. Thank you so much, GoDaddy. This is the first time I've actually been in this complex. I didn't realize all this was here. I guess there's like Amazon is all back here too, apparently. That's the Sunnyvale region right there, the secret Sunnyvale region for Amazon. Yeah, so we got a lot going on tonight. It's going to be a bunch of GPU talk. As usual, I'm going to probably blaze through the intro and what would be mostly my talk, just to get it out of the way and make more time for the other speakers. The first year or so of this meetup, I did all the talking, and so now I'm actually like letting other people speak, and you can hear other people. So, yeah. So thank you, GoDaddy. These guys have been awesome. They ask a lot of questions. They wanted you guys' experience to be awesome. They wanted you to see the water bottles and the, all that stuff, which is kind of funny because no one usually goes to that level of detail. Yeah, I'm a big fan of GoDaddy. I've got about 200 domains. I was looking today. I don't know what or why I have all these. I have a lot of Flink domains. If anyone wants them, you can have the Flink domains. I should probably offer them to my Flink buddies, the data artists and friends. But yeah, Flink by example. I don't like sell these to anyone. Like I had high performance Spark. If you guys know Holden Corral, she's one of the authors on that book. This is her third Spark book, and of course I just give these things. I don't want schmucks taking these, but yeah, what's one here? Flink for dummies, Flink for the impatient, Flink graph, Flink idioms. Yeah, that one's good. 6,400 Meetup members. Yeah, Jose contributed to that. You probably weren't a member until you flew here, right? Yeah. You remember?
I have my own meetups in Dubai.
Yeah, you're actually like one of the first people listed here, right?
Yeah.
There. Yeah, you're right. Yeah, how does that work?
I have no idea.
Why are you? Yeah.
Because I'm a paying member. That's why.
You pay?
You have to pay now to meetup to organize. That's called Meetup. Oh.
Okay. Oh yeah, that's right. They just set the bill.
Just
All right, yeah, lots of GPU talk. Yeah, we have Nathan Howell here from GoDaddy. Yeah, he's a TensorFlow contributor, Spark contributor, runs a super badass team here at GoDaddy. Talk to him afterward. I think you're gonna have a little marketing or like a recruiting spiel later, whatever, right? Yeah, and then Chris. Gottbrad. Yeah. I keep searching for you under like gold something. And
I won't come up there. No.
he was kind enough. I've been bugging these guys forever, right? Like from like the Nvidia Corporation to come talk about TensorRT. Yes, I have a lot of friends that work at like the Nvidia place, and nobody knows anything about TensorRT. They all kept pointing me to Chris. So Chris is going to tell. There's probably some people here from Nvidia that are probably going to learn about. Is Leo Tam here? Leo comes all these. Okay. Yeah. So Chris is going to talk about the new Pascal half precision, the FP16, and the INT8, and how that applies to machine learning and why this is okay. And let's see, a couple other metrics here. So 6,400 members. The GitHub repo that powers like a lot of these meetups and demos, at least from my standpoint, we got 1,300 stars. We got a lot of people here. I think Jose is probably right around here. Yeah, Jose is, I'm sure, on here. I've been to Dubai twice.
Yeah, there, left, one back.
Is it down here? No, it's right here.
Over there.
It's somewhere near, yeah, between India and Egypt. Yeah, so we got about 1,300 stars, which is pretty cool. People are asking a lot of questions, pinging us all the time. My Zendesk is blowing up. Yeah, actually Zendesk just blew up. Did you guys hear about this? Like anyone get an email from Zendesk saying, we're sorry that we blew up? So I'm taking personal credit for their blow up because yeah, so much support traffic's coming in. Yeah, that's a joke. So we've got this community edition for PipelineIO. So a couple cool things I've done since the last time I spoke here is we have a PipelineIO CLI, which to me is magical. There's this really cool project that came out of Google. It's called Google Fire, I think, and it can take a Python function and basically create a CLI out of it. And so this is how they do the G-Cloud and all that stuff. Yes, I assume anyway, because like it all kind of looks the same. Yeah, it's called Google Fire. So like check that out if you're interested in creating CLIs. We've got Scikit-Learn support. Have actually 2 customers right now working. They were all excited about TensorFlow, but their data science team is like, hold up, yeah, we just want to get our Scikit-Learn stuff deployed. So got the Scikit-Learn stuff for like behind a REST service, all that kind of thing. Right now we're using Tornado. Most people use Flask. I started using Flask and then realized that most people use Flask. And I started looking around and said, well, yeah, we have to do one up here, right? We're in the Bay Area. So I switched over to use Tornado, which is kind of cool. It's async. It's super complicated. It's not super complicated. It just looks different than Flask. Right, but yeah, that makes it cooler, right? Because yes, other people don't know about it. So yeah, check out Tornado. It's like blazing fast. Like I had zero faith that like Python was going to be fast at all, but it yeah actually does a pretty good job. Also, lots of GPU stuff. I'm gonna spend a few minutes talking about this recent like training thing I did, right? Like with the O'Reilly Media Company. We did, it's called High Performance TensorFlow yeah, in production, which is purposely generic because we covered both training and serving. So yes, out of that came these TensorFlow Docker images. I snuck in Spark and HDFS in there, which people seem to be pretty excited about on the webinar. So yeah, this is all out there for you guys to pull down. You can run it. Yeah, I'm going to mention this too in a second, but Google came through majorly. So they just released GPUs, what, like February 22nd or something, about a month ago. And I had been in talks with them about possibly using their GPUs for this class. There were about 350 people signed up for the class. Yes, I didn't tell them how many people were signed up. They said, oh yeah, I think we're going to be out around then. And then I said, we have 350 people, and they just spread me across a bunch of regions. So we had people from right, like Wisconsin connecting to, you know, Asia and Singapore and all that kind of stuff, right? Yeah, so they came through massively. It was flawless. Used the G-Cloud API because the like console didn't even support, right, like the Nvidia, right, like attaching at that scale. So you had to bust down to their G-Cloud like command line. So yeah, pretty flawless. I'll talk about that in a sec. You can sign up for this class. I think you have to be a full Safari member or something. But yeah, the other big news is, yeah, IO make money. And we now have a premium, right, this like premium version, which makes me laugh because I never thought I would stoop to this level of cheesiness. But yeah, you can email sales@PipelineIO, which just comes to me. So you can email Chris@PipelineIO and it'll go to the exact same place. But if you want to go that route. But yeah, we do actually offer some like pretty cool stuff here. Some of the things I had played with on like the open source side and then realized this is actually going to be quite a bit of work. So things like the Bandit testing of your model deployments, things like that. So all of the stuff that is there right now within PipelineIO, the straight up like model serving, all that stuff stays, of course. We're just sort of building things on top. Things like spot pricing, which is a huge Databricks feature, right? They support spot pricing. Yeah, this is now like commodity stuff comes out of Kubernetes. So it's just cobbling all these things together, right? Like together. Yeah, things like the circuit breakers are there in the actual open source community version, but yeah, we're gonna do some cool stuff there. Okay, so there's a workshop coming up. You guys can click on the link. It's basically going to be an expanded version of the O'Reilly one that I did. I can't legally use the same content, but these concepts are all open source, so we're going to cover a lot of the same topics. This is going to be online. Yeah, so you guys can go to the Meetup page, and it's good. Yeah, so everyone gets a GPU, right? Like just like the O'Reilly thing. We're going to focus more on distributed TensorFlow and training. What we're going to do is, so everyone that signs up, right, like each gets a GPU, and then we're going to link them together and then run some big training jobs. Yeah, so I've done this with previous workshops where we hook together all the Spark workers and then rip through a bunch of recommendations, things like that. It's pretty fun. So yeah, like we'll cover parameter servers. Of course, there's gonna be a lot of focus on like TensorBoard. If you notice here, you'll see green is the GPUs and this blue thing, or whatever that is CPUs. So yeah, we'll explore a lot of that. We're going to do some post-training graph optimization. So there's this thing called graph transform tool within like TensorFlow that takes a trained graph, which has a bunch of extra crap in it that's used during training, right? Like logging things out to make this nice, pretty diagram, things like that. You can actually strip that out so that when you go to serve, right, the model is much smaller. Yes, it's a lot faster on like the inference side. Yeah, one thing I kind of snuck in also was some CUDA programming. So yeah, like we're gonna do some more of that. That was actually the very first exercise for this O'Reilly thing. I think I freaked out a few people. Dropped them, they dropped the call pretty quickly when I was busting out pointers and the little, it's all the C memories come back, and school and hating life. And then we'll do some Spark and some Scikit-Learn just to make like normal people happy. Yeah, like me being normal as well too. I like that. All right, so yeah, this O'Reilly thing was really cool. There's I think 2 more scheduled. There's this one on May 12th. It's full. I just found out when I did the screenshot. So sorry, can't make that one. But we actually covered quite a bit. We do XLA. That's the accelerated linear algebra. So there's a lot of new stuff that's coming out of Google, right? That is like compiling things down to like LLVM and then natively going from LLVM to the native actual device, right? So the mobile devices, things like that. So like there's a lot of really low level stuff going on, which is fun because it kind of gets us out of the JVM, gets us out of Spark land, and actually like requires us to think through problems and not just run a few APIs, right? Yeah, if anyone watches Oprah, I'm from Chicago, I'm a big Oprah fan. Actually, I've never really seen the show, but my mom's a big Oprah fan. And yeah, so she does this like Christmas thing. Everybody gets like an iPad or whatever. So that was one of the slides in the O'Reilly thing. Yeah, this is the environment. Yeah, has anyone actually used this TensorFlow debugger? Yeah, have you used it? Yeah, it seems like super hokey, but you can actually like use your mouse and like click on things, and there's like a back button and stuff, but you can actually step through the training process. So this is good, for trying to figure out exploding gradients, right? Like vanishing gradients, things that are like causing you problems. You can actually step through. Yeah, but like you should check it out. It's kind of cool.
Is it actually better in practice than just logging?
Then just yeah. Like some of my hardcore like TensorFlow friends, they pretty much they were like ones like you, and then they started using it. And now they can't. So here's an example. What's cool about the XLA stuff, right? Which is so there's actually so this XLA stuff, the accelerated linear algebra, is a framework And there's a just-in-time compiler portion, and then like the AOT portion, right, like the ahead-of-time compile, where you can see everything statically, like compile. So you like treat XLA during training. So this is the just-in-time part. You treat it just like a device. So similar to how you can place things on a CPU or a GPU, right? Like you could also place them on XLA CPU or the XLA GPU, and that actually kicks in and gives hints to say, hey, this is a portion of code that right, like you should consider like compiling. So now this is kind of cool. Let me zoom in here a little bit. This is all on the Meetup page. I've switched from PowerPoint to Meetup HTML or whatever this is, markup. This is something, so what's happening here is that we want to visualize what this like JIT compiler is doing. And so these are actually GPUs. And this diagram doesn't really get any better when it's pulling up. But, so I'm using the Google Web Tracing Framework, which I didn't really know what this thing was. But you can instrument your like TensorFlow code to write out into this format that can then be picked up, and it's for like timelines, right? And showing placement on different devices. So these, this is GPU 0, GPU 1, whatever. The various streams on the GPUs. And then over here, so this is kind of before, right? So what this like JIT compiler is doing, it's similar to what Spark does when it's fusing together operators. It's taking multiple map functions that the simple developer just does map, because that's what you know. It's going to fuse those together into one physical, right, like Java method, right? That's how Spark works. So like similar concept, there's a whole bunch of operations here that can be fused together. This is how you instrument the code right here, and then this is what happens is like you get one block here. The times are not really to scale or the same scale, but yeah, you can actually instrument and see, right, that this is actually happening. To get this stuff to work, took me about a week of just going through pull requests and like GitHub issues. You have to like compile from source. So I've got all this out there. If you go to that like PipelineIO and then go to the GitHub repo, there's I think it's the O'Reilly.ml project or like sub project, and then there's high performance TensorFlow, and all the code, all the Docker images, everything is there. I don't think the slides are there. They're kind of weird about posting the slides, but you can access all the code, all the notebooks that we use. There are about 10 notebooks where we actually did all this. So don't try to do this yourselves. It's the most painful thing in the world. There's all these hidden features. I've also turned on a lot of the native CPU type things, right? Like, yeah, all those, yeah. So it's like pretty much as fast as can be. That stuff starts to get really, really specific to the hardware that you're running on. So this was completely tuned for the Google instances running Ubuntu 16.04. So yeah, all that stuff's documented. Yeah, here's some of the, yes, I mentioned graph transforms where you can take a trained graph and kind of merge things. You can strip the unused nodes. You can do batch normalization, folding constants, similar things to what you would do when you're going from like a sloppy logical plan to like a tight, right, like physical plan, right, like query plan. There's this sort of interesting one that's called remove like device. So this is when you train on the GPU, but you know that the target, right, that's going to actually be doing the scoring, right, like doesn't have GPUs. So you would strip out, right, the fact that you're trying to, right, like place this thing on some device that you know isn't there. That's physically a node within your, right, like TensorFlow graph that can be removed. Things like rounding weights, quantizing weights. Not going to go into too much detail, but if you have floats that are between a particular minimum, maximum, you can quantize and sort of put them all into, right, like 256 buckets, and sort of simplify. There's the like graph transforms there. Yeah, so at right, like runtime, this actually helps out quite a bit, right? It's still going to be, it's like a little bit approximate, like a little bit fuzzier than, but right, like definitely makes the model. So in my testing, I think I took there was a 90 meg model I was using. I think it was the Inception model. I ran the like quantization and then got it down to, I think, 22 megs. So this is right, like significant when you're actually trying to do these on cameras or the JSON like devices, that kind of thing, right, like from Nvidia. TensorFlow serving, yeah. So the rest of the stuff would be TensorFlow serving. It's kind of a high level. There's some inputs coming in, then things come out, classes, and then scores. Let's see. Yeah, so there's a couple optimizations that we did for TensorFlow serving. Of course, we got the GPU stuff working. TensorFlow serving will gobble up the entire GPU. We found this out the hard way, or yeah, I found it out when I was preparing for this class. There's a couple open GitHub issues. Actually, this is the Google guys asking the community. There's ways to actually limit, put like fractions, things like that. So it's not going to gobble up all the memory. But for these 12 gig, right, like GPUs, yeah, so right when TensorFlow serving starts, it just says, excuse me, this is all mine. But yeah, there's like a lot of mystery parameters. For TensorFlow serving, you have to build it from source. There's no, pip install or anything like that. There's a lot of people that get frustrated with this because this is all C++ based, so there's all these random errors, especially a lot of data science people that just don't want to deal with, these kind of stuff, right? Like these kind of compiler problems and linkage problems. I've got like a ton of, this is a hack based on this GitHub issue, things like that. So, but we finally got that. It's blazing fast, yeah, as you can imagine. Also, the other big optimization, I've talked about this plenty in the past, the request batching. So, essentially you wait 5 milliseconds or some, set number of microseconds. All of the requests coming in get batched into, one big matrix for that particular like duration. So, these are 2 separate requests coming in. Instead of doing these individually and passing them to the GPU individually and going across that slow bus between CPU and GPU, you can pack them all into one big matrix, just pad it with zeros, just do one big matrix multiply and get the exact same result. And because you know the offsets, right? Yeah, so you can actually do one big calculation and say these, top 2 go to client that's in, right, like Singapore, and then right, like the other one goes to Dubai. Something we actually ran out of time on, like the O'Reilly call, but yes, I've talked about this quite a bit, is using, right, like, yes, I came from Netflix. I like the Netflix open source, certain parts of it. Certain parts have been kind of, deprecated over the years, just not really relevant, things around Kubernetes, things like that. So I've taken sort of the, best pieces, worked pretty closely with the guys from Red Hat that had this project called Fabric8.io. It's like totally awesome. It fills in all the gaps that like Netflix would want, from like Kubernetes, but yeah, so Netflix has their own DNS or right, like sort of internal right, like load balancers and service discovery, things like that. So yeah, those Red Hat guys have been, yeah, absolutely critical. Yeah, here's Tornado. That's the logo. It's just like Flask, but more complicated and therefore cooler. Last but not least, there's a lot of TPU stuff. Not going to have a whole lot of time to go into this. I don't think the Nvidia guy, Chris, knows too much about the TPUs. There's a lot of comments in the meetup here. People want, the Nvidia people to know about this and have already done benchmarking, and like, we don't even have access to these things, right? But so yeah, please don't beat up the Nvidia guy. There was a TechCrunch article as recent as yesterday, and yeah, the day before was the Google blog. And this is something Jeff Dean, who's right, like everyone's right, like, yeah, he's like a tech Chuck Norris, basically. Yeah, everyone, what was the joke I heard recently where he like puts his pants on, not one pant leg at a time, but he does it in like log n time. Yeah, he actually does it for those people. Yeah, that was the first time he had heard that joke. He was like cracking up. He posted this. This is a paper that's about to be released. Yeah, I thought there was some snitch that like released this. I was afraid to put it on here, and then I realized the snitch was actually like Jeff Dean himself from Google. Kind of the mastermind throughout the years for like pretty much everything sweet that like Google has done throughout the years. Yeah, funny story about that same conference with the pant leg, like log n. Yes, I actually was in the bathroom with him at the exact same time, and I've never had stage fright like in my entire life, going to the bathroom, but I was next to Jeff Dean in that. That was pretty significant. I like didn't know what to do with that. And then just picturing the pant legs, we might have to swipe that from the video. Yeah, just a couple charts here. Yeah, obviously, this is Google doing their own benchmarks with their own software. Yeah, a couple good things here. Let's see, and then I think that's it for my stuff. So if there's time at the end, I'll do a couple demos. I just spun up my GPU instance, so I can show that, but I want to get these guys going. So Nathan's up next. And then, yeah, Nathan, if you can just kind of talk about your team a little bit. And yeah, how do we get connected? I think through Tracy, right?
Yes, through Tracy, who's online.
Yeah, hi, Tracy.
Hey, how's it going?
Thank you. If you have questions, ask me later. Or just email sales@PipelineIO. Not help@PipelineIO, because that'll crush Zendesk.
You guys hear me okay?
Yep.
All right, I'm going to try to take over. Not do Chris. Any chance you can close the
Unshare.
unshare? All right. So my name is Nathan Howell. I'm an architect here at GoDaddy. I've been here for about 3.5 years. I've worked in a variety of areas, mostly around personalization and setting up our big data platform. So that's why you'll see me doing work on both Spark and some TensorFlow work, as well as some other open source machine learning projects like Brushfire. Kind of get to work on a lot of fun stuff. What I'm going to be talking about tonight is work that I've been doing over the years with a few other people, a few at Bricks, and then a few other open source contributors on really revamping, rewriting almost all of the JSON handling within Spark and Spark Script. So not TensorFlow related, but there's a lot of concepts that I think will apply as well. So the agenda covered is this motivation of why we're doing what we're doing. Specifically tonight, we're going to be talking about JSON path, the query language, and then get JSON object. This is a class within Spark, which is the interpreter for that we use in Spark to evaluate a JSON path expression. We'll cover pressure combinators, so really how we get the expression into a form that we use for evaluation. And then hopefully we'll have some time to dig through some examples. So the background on a lot of this JSON work was really, Reynolds and going in and saying, like, opening up these bigger umbrella tickets, saying like we need to get Spark native versions of a lot of UDFs that were implemented or have been implemented for years within Hive. And he likes to, I don't know, I think he likes to bait me with fun stuff like telling it or either messaging me after hours saying, this is really complicated. What can we do? But beyond that, we actually do have some real reasons for trying to improve the performance of all the JSON handling within Spark. But here at GoDaddy, we end up using JSON for a huge amount of all of our event processing going into Kafka. Starts off as JSON. Eventually, it becomes something else, but for for any streaming queries, we need to be able to consume JSON at ideally the fastest rate possible. And the other aspect of being able to have a single job that most of the logic span can be reused between batch mode and streaming mode is that it makes it very easy for training pipelines to see exactly the same data going into the pipeline, regardless of if you're running out of HDFS or if you're running out of sparse streaming. There's been a few other improvements in the area. This is stuff that's been coming out in Spark 2.1 is this from JSON and to JSON UDFs, but while they're nice, they aren't quite as expressive as what you get with get JSON objects and JSON path in general. And then the other one thing there is just dusting off some of my old experience writing functional code. I was a professional Haskell programmer for a number of years. And this is sort of like the last fun or the last big project out there, really, where you get to apply real functional programming techniques, where it actually still it makes sense both from the code maintenance standpoint and performance standpoint. It's amusing enough for me. So what is JSON Path? JSON Path is a tool for picking parts of JSON out of a tree. It's really kind of a set of directions that says how to navigate a tree or a JSON object, if you will, and then grab some node within it. Sometimes more than one node. It's fairly limited in what you can do with it, and that's actually good for us within Spark. Spark itself can do so much more work that JSON Path could do. Like JSON Path does support some amount of aggregation, but we can use Spark for that instead. So like what Hive supports is really just the most basic of operations. Has this notion of starting at the root of an object, being able to select a specific child within a node. So if you have a JSON object that has 6 fields, you could say, like the field that is key food. Of course, indexing into arrays and this notion of child cards, or you can use this to flatten out arrays or to grab all fields in an object. There'll be more, let's say, more interesting operators like how we can support number supporting, which made my job easier. I guess that. So, really at the core of this get JSON object class is a very small virtual machine that supports two instructions. One that does this lookup of a field by key name, and one other instruction that supports looking up a index within an array. This idea of building instructions like a simple virtual machine to solve problems is super powerful, and ends up it's also used for a lot of the same reasons within Spark SQL. This is the Catalyst engine within Spark SQL. Follows the same model, as well as TensorFlow itself. Very much just DSL based. Everything that you're doing within TensorFlow is describing operations that you would like to run. TensorFlow runtime that basically is an interpreter, or in the case of XLA, that's Spark SQL. All the optimization that happens is on this virtual machine or DSL, if you will. The other goal of the implementation, unlike Hive, all the work that we've been doing within Spark has been to support incremental or streaming processing of JSON. It has a few benefits, mostly that we're not storing an entire large JSON blob in memory, but also that we can throw away everything that we don't need as soon as we know we don't need it. So the Jackson library that we use for JSON processing, they call this streaming. A lot of people confused occasionally, like, is this related to Spark streaming is not extensive. For whatever reason, they ended up calling it exactly the same thing. But the overall goal of this project was really just to support just the bare minimum of JSON path to match, not just Hive's implementation, but to become tests for all of their test suite tasks. I think I already talked a little bit about this. That when I read through the spec, you look at what operations they support, and to build a DSL or VM interpreter for this spec, kind of logically need to figure out what the expressions support or what they allow you to do, then to map these concepts to a data type or some kind of values that really ties it exactly back to the concept of what you want to accomplish, rather than what the user read. In this case, it's pretty straightforward. We don't have predicate support or anything else. That expression with the JSON path, like indexing into an array, then just internally build up an AST code that says we want to do a subscript operation. And in subscript, we'll grab index. We have the equivalent operation for doing field lookups. Now, the problem with trying to maintain compatibility with Hive, though, is that the Hive implementation doesn't really follow the JSON path spec. It doesn't really exist either. But there's a lot of fairly non-standard things within their implementation that I found out well after I had started coding. But got in all the way to the point where test cases were passed, and then a bunch of them started failing. Are very unusual sort of data and query combinations. It took me a pretty long set of mornings to figure out how to work around them. But none of this stuff is bugs since they didn't have a spec. So this idea of building interpreters and DSLs is, I think, makes it very easy to think about how you solve problems. We have this other problem where the expressions are coming in as text, and we'd like to turn that text into an AST. So my tool of choice for stuff that's not performance sensitive is to go towards parser combinators, which at the core are built on combinators, which are basically just, most people think of this as function composition, but it's just our combinator at the core is just a function that takes values in terms of limited values, but typically we talk about them in the context of parsers or function combinators. But really anything, you're not limited just to that. TensorFlow fold is another new and interesting example of a combinator library that works with blocks. Well, they call them blocks, but like an RNN could be a block, and like a fully connected layer to a block. Then the combinators are how you describe how evaluation happens, rather than needing to thread through all these kind of states together in the control flow logic that you would in base TensorFlow use case, or even using like the contribute layers package or carrots. Another common example of a combinator library out there would almost be Java's completable future, but there's an additional restriction that the combinators shouldn't have no side effects. We want to be able to describe what you want done, and then later on actually trigger the evaluation of it, where completable future starts generating new work right away. So if you wanted to chain futures together or run 5 futures in parallel, collect the results, that operation you could think of as a combinator, but because it starts doing I/O right away, it's really time. The whole idea, though, is that you want to be able to think about how you build up a solution to a problem, starting at the very small pieces of logic, and then combine them using these combinators into a bigger solution. The parser combinators, you can think of them as like the smallest building blocks within the combinator library. Particularly in Scala's parser combinator library, is that the small bit there is usually a single regex, but it really could be a single character match. But it has a lot of other benefits that you can take. You basically get to build regexes up from smaller regexes without doing string concatenations. So you can get these small units of a regex, which would be something like, I'd like to match something that looks like a string, but then I'd like to turn it into a string that looks like an integer, but then actually turn it into an integer. We can build test cases up around this parsing, and then you get this reusable block parsing as an integer, just like you would normally get in a Lexer library, for example. But it's all purely within, in this case, Scikit-Learn. You can just really imagine that a lot of parsers that people do use, and I know this is fairly common for machine learning pipelines, the people doing web crawling and web scraping or dealing with user data but it is just really convenient to be able to test some portion, something that maybe matches an IP address or something that looks like an email address, be able to test that, make sure it works, and then you never have to worry about, like, when this gets rolled into a larger regex, that it doesn't work right, or that there's matching the wrong things, or that you have match groups that are changing positions, things like that. Kind of famous quote.
What's that?
And so in this way, like, the parser combinator idea is really a solution to this. You're building first-class parsers, but they're composed of smaller regular expressions that you know work right.
That has been a dumb question.
There are no dumb questions.
I don't write code like you do.
Okay.
So therefore, my question is more theoretical. You used three terms that was confused. You talked about IRs, you talked about DSLs, and you talked about parser combinators.
Yes. I did a bad job of picking one terminology for DSL. So a DSL is a domain-specific language, kind of a common term. From the compiler side, the same idea is oftentimes called an IR, or intermediate representation.
Like LLVM, for
Like
example.
LLVM is one example. And within a lot of applications, there's multiple IRs. It's very common in the compiler standpoint. In this case, we also have multiple IRs that you're starting. Well, simply enough, we only have one IR in this case, but by the time it actually executes, there's multiple IRs. Right? We have the JVM involved, which has more than one IR, as well as their support. Simply getting back to kind of what a parser combinator really is just a function that takes a string as an input and then returns a value of some type, and then whatever it didn't end up parsing. So it's a really simple concept. It has a few other functions that we rely on to compose them, but really it has a name that sounds a lot more complicated than it actually is. All the other functionality, or a very large portion of the other functionality, is it comes from like a regular expression. So, like the notion of an alternation operator within regex, we have exactly the same operator with with a parser combinator, which we call altercation, which would choose between two potential parsers. All right, so I guess I can do a few quick examples. I did sort of want to run through some of the actual code. One of the more common terrible rejects is that end up on Stack Overflow is trying to match an IP address. Scarily enough, this more or less matches an IP address. Say 4 lines here. And what this regex is trying to capture is that IP address octet is going to be basically a single byte value. So its range domain is between 0 and 255. And like regexes aren't really designed; they're not designed to do numeric pattern matching. So all this terrible code here is really to work around that we're using a regular expression to do something that's not good at. The same idea moving over to parser combinator. I will first kind of start with the same terrible regex as a base, but at least we only have one version. We have something that takes a string, parses one octet out, and the syntax here says that you have a parser that returns a string, and we can take that string, we can map it to a byte fairly easily. We can define one other portion of the parser that accepts a period. And then we can do something more than what you can do in a regex, is that we can turn this initial string into an actual, like an INT8 address, like a real instance of a class. So that's kind of it's a very simple but powerful concept that we can build on. That we can start with these very small building blocks and work them up into instances of types that are actually useful, not just strings. And the combinator part of it is that once we have an INT8 address, so this dotted quad, we can reuse the parser to go, say, parse a address with a port, and then turn this into an INT socket address, an instance of a class that contains both an address and a port. So it's a lot of good code reuse. You can test them individually. Pretty cool. But you're not limited to just regular parsing strings. Using regexes to do this byte validation, we can use classes, just regular Scala code, to do the validation. So we could say we'd like to parse any string of digits, convert it into an integer, filter it to make sure that we're only getting things valid bytes before we cast it to a byte. We get the same logic, but we don't have to mentally jump through hoops to figure out how to legally parse the textual representation of an integer. So a little bit more concise, potentially easier to understand, but certainly less regex do. And the same bit here. We did the same thing with JSON path. So we had to define sort of what like the root character within JSON path is, this root operator, which is a $. We can easily parse values of their longs. And we can, as we're parsing, turn the expressions into values of this AST that we're later going to evaluate. They're much simpler than I should probably show you. compare this to what it looks like in the Hive code, the Hive code is 2 or 3 times as long. Really hard to understand what it's doing. And it redoes this a lot of operations over and over because they don't convert it into this intermediate form. So like, very simple ideas, but they're more concise, also easier to understand, easier to test. And in the end, the implementation ended up being maybe a similar amount of code to Hive, but so much easier to follow, at least in my opinion. I think that's more or less all I had. I didn't through a lot of the code too fast, but if you want to look at more code.
What were the like trying to get something committed into Spark? How did that go? So like, how much time did you actually spent writing code? Yeah, because like this happened to me too. When I committed, I spent like a month, kind of off hours, and then I spent like a month just the coding style and the comments. And all that.
This one was surprisingly easy.
Yeah.
I've also found that the bike shed problem runs deep everywhere. We started work on this. The whole thing took like 3 evenings, maybe. And the biggest hurdle that I ran into was around the Spark's testing infrastructure more than anything else. So in the end, I could never get it to actually merge because there was so much other work that needed to happen within the way that they test their high compatibility layer that people that knew the testing infrastructure had to help out. So there was Davies Liu and one other guy.
Was it Nicholas Shamathama?
They ended up doing like the last series of commits. But it was very, very easy. So code review feedback was sort of a day or two turnaround. So you compare that to some of the work that I've been doing like in the last 6 months, that it was 2 months of code reviews, turnarounds.
For Spark or for
Spark? For Spark,
yeah.
Yeah. So that they're definitely upping their level of strictness about coding style.
Yeah.
Which is good. I think for a project this large, it really does everyone a service to have a consistent style, but it makes it difficult as an open source contributor to have to do a lot of round trips. Equivalent sort of patches, the TensorFlow side, more about Python compatibility and having to test every single patch that you want merged against Python 2.7, 3.3, 4, 3.5, 3.6, dealing with all that stuff. It's way more of a burden on me. I'm not a Python 3 guy. So yeah, overall, pretty easy.
What were the TensorFlow? Yeah, like you told me on the phone a couple weeks ago, but I don't remember.
We do, well, my background for machine learning is really in text processing. So dealing with, say, building TensorFlow examples for a pipeline queue.
Yeah.
If you're emitting like a lot of sparse vectors or text features into a training example, they're huge. I think a TensorFlow example like this, if you're starting with an image, for example, or like an audio snippet, is already compressed. Like they internally decompress JPEGs on the fly with part of the pipeline, I'm sure.
Yeah.
You gotta know about this.
Yeah.
But for text, that wasn't the case. They eventually added support to decompress compressed TensorFlow examples, but it wasn't well tested. They missed loads of test cases. So.
And like the term example is like it's like a row going in, right? It's an example, not like a code example.
Right. Yeah. So I'm talking about just like it's the TensorFlow example protocol buffer, which contains just features that you would normally feed into the top of your model. So that was more of the work I've done around that.
Yeah, that's one big thing that we covered slightly, but it's more like more comes into play for like the distributed TensorFlow. Is that if you find yourself using feed dict, which is kind of the basic example, right? And then that's just when you create an array and then pass it in, and you can run it all within one process. Like that doesn't work in real production. So what you want to do is have queues, and these queues also have pipelines. So you could actually process data, right? It's in the background. Queues have these, like queue processors have their own thing. It's how you can saturate the GPUs and saturate the CPUs, things like that. So if you're not using queues and you have a production pipeline with TensorFlow, you should definitely use them. Because if you're not using them, you're constantly going between C++ and Python and all the bad, nasty serialization. Yes, everything has to go through the master. Yeah, there's all kinds of downsides. So, whereas with queues, each worker node gets a batch from the queuing system. That like queuing thread pool actually breaks it up into batches, and then each batch goes to a GPU or a CPU separately in parallel.
All right, so now on a little bit of a TensorFlow.
Well, it's more TensorFlow.
Yeah, I was hoping to have more TensorFlow related stuff to show, but conceptually a lot of like how the combinators work, how the couplers work is very similar to how TensorFlow works, like TensorFlow fold works. So
I don't know too much about the folds. Can you talk more about?
So what TensorFlow fold is?
Yeah, like I don't remember using them like directly, I guess, right?
So TensorFlow fold is a separate project that uses basically combinator libraries to build your overall model of these smaller pieces.
Gotcha.
And it's extremely powerful for dealing with more complex RNN model architectures, particularly for like hierarchical LSTMs, for example, the amount of code that goes into the training. Hierarchical models like a hierarchical char to vec, word to vec, paragraph to vec type architectures are really difficult to express in TensorFlow, and they tend to perform very poorly because of how dependencies work between layers. And TensorFlow fold does some clever stuff through the covers to change to a much different model structure without a different primitive operator that they call a loop that gives them better parallelism for very complex RNNs.
So yeah, so that clears the pathway then for the model parallel training, where like typically when you're doing like parallel training, it's the same model put onto each node, and it's just operating on different partitions like Spark works. But for the model parallel, each worker has part of the model, and does fold give you that composability or something?
Like this, so the question really is: does fold make it easier to parallelize across machines? Because it captures a higher level dependency structure between portions of the model, so it's more clear what should live together.
Okay.
But right now, they're not doing any automatic parallelism across machines or even with a single machine across GPU. So it would help, but I don't see that making any difference really to that.
Yeah, because that's always the trick, is to figure out where those dividing lines are, where the model can be broken up. So that was the first thing that came to mind.
Yeah. The more of a high-level representation you have of the model, the easier it is to understand how to parallelize it across machines. That's the same way that why we can get better parallels within Spark SQL is the operators that we're running are so much or high level. So you know if you're doing source, what that means. If you're only dealing with map partition solutions, for example, they have very little idea of what you're trying to accomplish within the model or your program, so they can do less optimization. Okay, so I think that's basically what I got. Okay, thank you guys have really helped.
If you guys ever go to like Strata, right? That guy Yin is he's awesome. Like, yeah, he was one of like so Michael Armbrust from Databricks is like the main Spark SQL guy, and they hired Yin and was just like an instant like duplicate of clone of Michael Armbrust that was able to pick up. So yeah, he gets a lot of really cool projects and speaks about them all the time. Yes, I don't know if like JV speaks also, but yeah, I think he's good too, obviously. But, yeah, Yin's good speaker.
As far as GoDaddy recruiting stuff, here we go.
Oh yeah.
Steve around. And also available to give out information about coordinators, so once they declare and all that.
Chris up next from Nvidia.
All right.
Oh, you came all the way from Sunnyvale.
That's right. Down around the Safeway, El Camino Real. It was a tough travel.
Still took you like an hour to get here, though.
No, not too bad. Thanks very much. So it's my first time attending this meetup, so it's exciting to meet you all. I'm going to talk, so let's see, a little more introduction. So I've been at Nvidia for about a year and a half. My background previous to Nvidia was I used to work at RogueWave Software, and I used to product manage, and I did a little bit of engineering with some of my code in the product. TotalView, the parallel debugger, so you can actually debug across a big hyperscale machine, for example. So I have a debugger background and C++ background and things like that. Since coming to NVIDIA, I actually came to NVIDIA to do kind of high performance computing. We have a very strong presence in people building supercomputers and doing models of like galaxy structure or protein folding or things like that. And that we still do that. That's awesome. But the hot thing in NVIDIA these days seems to be deep learning. So I've gotten swept up into the deep learning craze. So I'm one of the software product managers in the accelerated computing group, which again does high performance computing and also deep learning. I've actually got a colleague here, William over there is on the hardware side. So I'm a software product manager, and William is one of the hardware product managers. So he manages some of the hardware you might use to do what I'm talking about here. I'm going to talk today about if you've taken the step of creating a neural network and you want to run it as fast as possible, have the best throughput at the lowest latency in production. Obviously, you use a lot of people. How many people here are doing deep learning? How many people here who are doing deep learning are using GPUs to do the training? Okay, actually surprised that the other folks are not training on GPUs. I find most people leave their hands up, right? Most people use GPUs for the training because the training is so computationally intensive. You know you need the speed, you know you need the performance to do training. If you have that same kind of need for inference, if you're gonna infer on every image that comes through some big data pipeline, or if you need to have immediate response. I'm talking to a lot of automotive folks because they have a very strong need for an immediate response. Something jumps out in front of you, you want your car to respond as quickly as possible. TensorRT is a software you use to do that. So I'm going to talk about a little bit of introduction about deep learning, talk about TensorRT. I'm going to talk about one of the techniques we use. So TensorRT generally does optimization on your network for inference. So there was earlier some reference of stripping out some of the stuff you only need for training. This does that, and then more optimization. But one of the optimizations that we do, which is, I'll show how significant it is in the performance, is to use reduced precision. So FP16 or INT8 representations of your data. And I'll briefly talk about if you want to put that in the cloud, I've got a REST engine example that we can talk through. I'm going to do a little bit of code. It is C-like code, so there'll be a reference to malloc in there, I think. Hopefully no one will run screaming from the room. Okay, so introductory stuff. You guys, this is kind of marketing slides at the beginning, but it's always good to level set. What are we talking about? The kinds of capabilities that people, I think a lot of people want in software as a service kinds of applications in the cloud are basically, a lot of those can be powered with deep learning. So better recommendations from Netflix has a really nice material advantage to you as a user, and then to companies like Netflix, for example. How does Nvidia play in that? Well, we make GPUs that just do that really, really well. So you can do things like replace 1,000 servers with 16 servers, and save the world a lot of energy costs, a lot of carbon cost, have better performance, and actually save yourself a little bit of money if you're scaling up to that level. If you're doing lots of deep learning training arrangements.
Can you go back?
Sure.
Is it more expensive? Less expensive.
Less expensive.
Less expensive.
Each individual node is more expensive, but there's a lot less. Okay, so I'm on the software side. So the software that I'm creating or helping the team create is part of our deep learning SDK. So we want to have a bunch of different tools that help you guys actually train neural networks and then deploy those neural networks. So it's the full gamut. I'm not going to talk about all the things on here, but I guess the main thing is we work well with the community. All of these different training frameworks are GPU accelerated, at least in part. And so there's things like TensorFlow on here. So we work a lot with those folks to make sure that they have good implementations that will take advantage of the GPU. And the one that I'm going to be talking about is this one down here. So it's one of the pieces, not the whole software. Okay. So what is TensorRT? TensorRT starts after you have trained a network in whatever training framework you prefer. TensorFlow might be popular in this crowd, but there are others. And I'm not going to talk about how you do that training, but at the end of the day, you have a trained neural network. And for thinking about TensorRT, I want to encourage you to think about your trained neural network as just a series of mathematical operations and a series of weights. So you've got kind of a graph representing the structure of the neural network that you've trained, and the hard work of your training was setting the values for all the weights. Right? That's your secret sauce. I mean, there's maybe some secret sauce in choosing the graph, but the thing the training ended up setting was the weights. So you bring those two things together. So some people will talk about my TensorFlow model or my Caffe model. That's the implementation that got you to those weights. But the model itself, your sort of IP, your special sauce is how are the layers connected? What's the math going on with those different layers? And then what are those weights that are going on?
A lot of trial and error.
There's a lot of trial and error. But the end result of that can be expressed concisely as this set of connections, this set of layers, this set of weights.
But you don't really know what caused what.
No, not necessarily. But you do have something, hopefully, that you have some sort of function at the end that you can use to measure whether you've got something that's working well or not. Right. Okay, so you bring that into deployment. So TensorRT becomes the environment that you run that neural network in. And it's compatible with all your different training frameworks, but it isn't all your different training frameworks. At least that's the sort of base way of using TensorRT. Now, it is a library. we're sort of approaching this as software engineers. So we're building a C++ library you can run. You can wrap it in other things. So the idea has occurred to us, and this may happen at some point. We could put it in TensorFlow serving, for example. But we're probably trying to provide a really low-level thing that you can put anywhere, right? So if you want to just use TensorRT and you want to control when it starts and when it stops and what it does from within your application, you have all that power. We're not taking anything of that away from you. It's designed to support the whole range of different GPUs. So data center GPUs like the P40 and the P4 and P100, automotive GPUs like our Drive PX, and then the embedded like the Jetson boards that go in robots and drones and things like that. So TensorRT runs across all of those and actually runs very much the same across all of those. We don't have a separate version. These two are ARM-based, so we actually have a separate build, but it's not like a separate, there's not a lot of features that are turned on for one or the other. Okay, I think that's the basic idea that I want to talk about here. TensorRT's reason to exist, its soul is performance. So on my what is TensorRT slide, I go ahead and gratuitously slap a performance graph up there because that's why you use it, right? You're gonna you want throughput, you want performance. If you just have a few images that you want to, or audio clips, or stock traces, or text that you want to look at just a few times because you're kind of a researcher, you probably don't need to use TensorRT. You can do that in your training framework. If you want to take some Internet of Things pipe that's pouring into your data center and now do something smart with it, that's where you want to use TensorRT because you want that throughput.
Can I ask you a question?
Sure.
Just a basic question.
Mm-hmm.
In the software SDK that you are providing, the TensorRT, is there an OS support toward learning? You're going to talk about floating points, etc. But does OS do something to speed up learning?
So I think you're asking, does the operating system you're working on matter for the deep learning aspect? So most of the stuff that we've been doing with TensorRT has been really around Linux as a starting point, but we are looking at porting it to other operating systems, and in terms of the performance impact, I would expect those to be very minimal. So I think that a lot of the heavy lifting that sort of impacts the performance occurs on the GPU, and our software is very much operating system agnostic at that point. Thank you. I think if there's any exceptions that could crop up. I can't think of any right now, but so I think it would be very, very independent of that. Okay, so what this is showing here to explain the graph is this is GoogleNet, one of the sort of standard networks that we've seen talked a lot about. So it should be kind of a known quantity. The blue bar here is CPU performance. That is a E4 2690 V4 2.6 gigahertz with hyperthreading turned on, and it pumps out looks like about 100 images a second of GoogleNet. The lighter green bar is our P40 GPU, and in the normal FP32 mode of use, you can see it's already giving you some pretty big performance gains. That's using TensorRT, so there's some software optimizations we've done, but it's using the FP32. And then we turned on the INT8 for this taller bar. I'll come back to the INT8, but my point that I'm trying to get across here is that the GPU, again, it gives you really high throughput, really low latency on the small batch size, and it does so pretty healthily with FP32, and you can do that on any of our GPUs. You can go back to the K80 or even the AWS's G2 instances. Those all have the FP32. The latest GPUs we have this INT8, so that's kind of a kicker, which gives you extra performance in the latest generation. I saw a hand up and then it went down. So, did you have a question?
How does it compare to like Cafe or TensorFlow?
I will show a plot that does a direct comparison later on. Yeah, so I think we'll just come back to that rather than generalizing something. The other thing that, to mention about TensorRT for deployment is we were thinking as sort of software engineers and thinking about the use cases. I mentioned the automotive and the embedded and the data center, and we're thinking you probably if I'm going to go deploy something out at scale to help back up a big video streaming service, or if I'm going to put something in a car, I'm probably not going to bring extra dependencies. I probably don't want to have other stuff in there that's not needed for actual inference. So another thing we do with TensorRT is it's sort of very self-contained, it's very limited in its memory footprint and its dependency. So rather than bringing TensorFlow or Caffe or Torch and all of its dependencies, you bring your model over and you run just something simple. That's the other aspect. In addition to performance, there's sort of ease of getting the data in and the ease of running once you've got it there. Okay, so workflow. Am I pacing this okay? Is everyone kind of following along pretty well? Okay, good. So in terms of workflow, I kind of had a really high level version of it before where I had training and then inference, but this breaks it down a little bit more. So you start with your training framework. Again, the output is this neural network. I encourage you to think about that as the math, your neural network encompasses. You're going to make some decisions as you go into the optimization. You're going to basically say, what batch size do I want to optimize for, and what precision? And then there's kind of an implicit choice, which is I'm going to do this optimization on some GPU. The way TensorRT works is it tunes for that machine, and it does it very empirically. Neural networks have the characteristic, at least all the ones that we've encountered and supported so far, have the characteristic that every time you run them, they run pretty much the same speed. There's not a lot of ifs and elses. It's just a bunch of matrix multiplications, right? A bunch of data movement, matrix multiplication. And that tends to be very reliable. It's to repeat. So we can actually do an empirical optimization. So TensorRT has kind of a library, a massive library, in fact, of optimized and in some cases fused kernels. Some of which will, so if you think of the kernel that does a particular layer, some of which will work really well if you have a lot of output channels. Some of which will work better if you have a small number of output channels. So we have kind of those in our bag of tricks. You set a couple of parameters and you feed in your neural network. TensorRT will run over that neural network and it will say, okay, I could use any one of these five algorithms, and we'll actually do auto-tuning. We'll try them all. With random data, matrix multiplies don't care whether you give it valid data or invalid data. They just the performance will be the same every time. So we can actually, without just on kind of random data, just as a part of our optimization process, we can see which one of those library of optimized kernels that we have will run fastest for you. That gets bound into this plan. So you end up with the best performance for your network, with the geometry that you chose, for the math that you chose when you input, that's possible on that GPU as part of that plan process. We don't repeat that. That's not that's once you've done that, the plan encodes this is the set of functions, and it'll give you the best performance. Does that make sense?
The question is that you're not doing a training, are you just like
this is all after training.
after training? So basically, you just do the forward path.
Yes, this is just forward path. Yes, so you've already trained. You may have done some choices in training to reduce the size of the network, and that's not a bad idea. But we're not going to change this. Whatever you express in your network, we're going to run that. We're going to run all the operations that asks us to. But we're going to do them in the fastest way that we can. We might fuse some kernels, which gives us more work to do at one time, which is GPUs are really good at that, right? We want more work to do at the same time. And it'll do all that under the cover, but it will still do all the operations you ask for, and it'll do all in the right order. That make sense?
Yeah.
So there's no retraining, there's no going back. It's not going to suggest, oh, hey, go back and retrain something.
So it's like you have suppose Caffe train model or Caffe model 5.
Sure.
It's concepts. You are doing a classification on, so you're trained for a cast, different cast classification. You input one image on the Caffe model. You're talking about that part? Inference classification?
Exactly, yeah. This is that part. After you've already trained, after you've got a model that can recognize all the classic cars, that would be a great model. This is, you take that model, you pass it through TensorRT, we'll generate a plan. You can save that to desk or just go ahead and use it. And then you can start passing in images, and it'll tell you as quickly as possible what kind of car that is.
So there's a new model output after TensorRT that in which we have to input our image, new image.
This is TensorRT, and it uses the plan that was, so these two things are the same software. I just have them repeated so that you use this one for inference and you do optimization for this one. And the reason I split them is because for deployment, you might just use the runtime, right? The idea is, the other one was, I guess, in your development environment, you'd want to validate that, hey, it gives you the right result, right? But, hey, it looks like it's working right. Now, in production, and the idea is you get rid of all this stuff in production. You've already got your serialized plan. We've already done the measuring of our functions, so we know which functions are going to give you the best result. We don't need to remeasure that. And you can just load in a data file into TensorRT, minimum requirements in terms of disk space and memory space and extra stuff you need to load, packages you have to keep up to date and make sure they're free of security vulnerabilities. Just load this in and run it.
So can the optimization step just be thought of as finding the most optimal forward path once it's been trained? Is that okay?
Exactly? Was there the hand that went up and came out?
Around same lines. Like, what are you optimizing for? Like, can you give a sample plan? Like, it doesn't seem like you are optimizing the model itself. It's more like related to hardware related.
Exactly. We're doing kind of hardware optimization. So we're allowing you to squeeze every bit of throughput that you can from a GPU for the model you've asked us to.
So can you give like an example plan? What would the plan compare to?
So the plan we could comprise, so I think you're asking kind of what would be some of the optimizations? Or
rather simply, what's your optimization objective?
Our optimization objective is the highest throughput for a given batch size. So you tell us batch size 8. We are going to find the set of kernels that will, for the neural network you've given us, allow you to run 8 images through and give you the result in the fastest time on that hardware. So it's performance.
Is it in similar lines with, like, in the previous, in the initial presentation, we had a matrix example where like two matrices get combined for a single operation.
Yep.
Those things.
It's that kind of so the batching that we would do here wouldn't have a bunch of zeros.
Yeah.
It'll be more efficient than that, but yeah, we'll do batching as well. This system has another dimension for the batch size. And you can, it's worth noting, you can fill that batch or not fill that batch. Once you've set the batch size, the point of the batch size in this level is that'll be the maximum size that we can accept because that affects the buffers we need to set aside. You know, our plan determines how much extra space needs to be there for the activations. Because we're doing that whole batch ideally all at the same time, right? We're not going to break it down and do the first one, second one, third one. We're going to push all of them through the GPU at the same time. So that means we have to set aside space to hold the activations at every layer, the maximum number of activations that we need at any of the layers for all 8 to go through the GPU at the same time. That's one reason you need to determine the batch size. The other is we'll optimize for that. So we're kind of guaranteeing that if you give us that many images, we will or input samples of whatever other data type it would be. If you give us that much data at one time, we will push that through the GPU as fast as that can happen. If you give us less, it'll probably be a little bit less optimal than if you told us to do less. Does that make sense? So we're you asked earlier what our optimization objective is. It's for that batch size performance. Make sense?
Accuracy and performance.
Well, we never want to give up on accuracy. So, yeah.
But you would also be dependent on CNNs that you use, the number of layers you use.
Yeah. Those aren't going. Those are part of your plan.
I see.
Or those are part of your input network definition. So we're not taking any of those away or turning those off. So you tell us how many CNN layers. You tell us what the weights are. We use. We're not getting rid of any of that math.
But the greatest challenge, and this is a genuine question, is in training.
Yes, that's true. And we have great software for training. I'm not talking about the training software. Yeah.
So putting it in another way, given the same random test sample,
I'll come back to you.
And the same network, irrespective of the plan, the accuracy will be the same.
Given the same network definition and the same, what was the second thing?
Sample, random test sample, like images, set of images.
Yes.
Test. Every plan will give the same accuracy.
Yes, modulo a little bit of, when we talk about the reduced precision, I'll talk about a little bit of a modulo to that, but the first order, yes. And there was a question over there.
Yeah, you mentioned, maybe I'm a little confused. You mentioned that, they look at your batch size to determine how you actually do the test. But usually batch size is you do it on the during training time, right? Yeah,
there's two concepts of batch. I think, so it could be wrong. I think there's two concepts of batch here. One is the mini batch that you use during training.
Yes.
And that's an important hyperparameter. It helps you avoid overfitting and local minima. And then there's a concept of batch at execution time. That's the one I'm talking about here, which affects your latency. So if you have a lot of data that you want to pour through, so think of data at rest. So you have, you're working a mapping service, and you have a bunch of satellite images of Africa or something like that. And you want to find all the roads and all the lakes and all the I don't know what else, geological formations or something like that. That data is already sitting there. You probably want to pump up your batch size relatively large, because you're going to just sort of chew through that. You don't need an individual image to be processed super fast, so you can wait for it to finish 100 to 128, for example, at the same time to get the best throughput through the GPU. So the batch size I'm talking about here is how many are you pushing through the GPU at inference time at the same time, and the main trade-off that gives you is latency versus throughput. You'll see on the graphs that I'll show later that the overall throughput is usually highest with the large batch size. But if you were to, you wouldn't want to do that in a speech sort of pipeline. So if you were trying to do translation, you wouldn't, or video, right? There you would probably be more in a latency bound domain. So you'd want to choose a small batch size. It might not be one, you might choose 4 or 8. You might take 4 little chunks of audio, which might only take 0.4 of a second or something like that. Push those through an LSTM or something like that at one time. But you probably wouldn't want to wait for 100 little bits of audio, right? Because then that would be too much time for your response. So that's the batch size I'm talking about. Does that make sense?
Yeah, it makes sense. Okay. Another question I have is that, for the network you're supporting, this is supporting like all types of RSTM, RNN, convolution, CNN, everything, or is specific to one function?
The sort of product goal is to support everything. The reality where we are with version 1 out and version 2 in development is we support convolutional neural networks really well. And we are working on some of the basic recurrent neural networks. We're doing LSTM and GRU first, and we know there's lots of others. So, but in the long term, we should support pretty much at least all the commercially important categories. There will always be researchers that will come up with crazy networks that we probably won't have support built in for. So, yep.
I have a question. What if you want to update your model? Like update the model. So you just need to update the storage plan file, right?
Yes, exactly. So you would basically, this could be, I would think of this as being the sort of put this into the pipeline of going from your training to your deployment. If you do retraining, you would just sort of pass it back through this. This step is actually pretty quick. So for a desktop GPU, when you're not doing INT8, and I'll come back to why INT8 matters, this is usually like 30 seconds. So it's not a long process. Usually doing the training takes way longer than that, right? Even if it's an update training. So it's a relatively short process. Yeah, I can talk about what's in theory possible in the future, but let's just leave it there for now. Okay, so a little bit of code. This is importing a trained model into TensorRT. Again, we have a C++ API for this right now, because we're sort of starting as sort of software engineers, and we're thinking production. There has been a request to maybe put like a Python wrapper around this. That's a reasonable thing to do, which we're looking into. So right now it's C++, and you basically instantiate your objects. You feed in your network definition. This is looking for a cafe model file, and it parses that and creates an object. Which this is which basically gets passed down. Here you set your batch size we talked about, and there's a workspace size, which is basically we have some algorithms. So again, in our library of different options that we sort of root through and find the one that runs fastest. Some of them will run really fast, but they're kind of doing a space-time trade-off, so they may use more memory. So depending, you kind of know whether you want to give us a lot of workspace and maybe take advantage of those algorithms, or you want to be more restrictive in the use case because you want to run have lots of models in memory. So you want to restrict our workspace a little bit. In which case, we'll use one of the other algorithms, which runs a little slower. So that's up to you to set. I should have put that on the previous slide as an input. Thought I had okay, yeah. If you are starting from something other than Caffe, or you don't have an easy way to port your graph definition or your network definition into Caffe prototext format, we have an API that you can use, and basically you just iterate over your layers. You tell us what your layer type is, and add it to the graph. Now it's connected. So you loop over, you'd be making calls like this. This isn't the full API, it's just kind of examples. We are looking at a streamlined parser like the previous slide. Currently have for Caffe. We hopefully will have for TensorFlow in the near future. So, yes?
In the previous slide, where you are attaching the Caffe model file, where you are referencing to the Caffe model file. The main model, the Caffe model file.
That's in here. A parser parse.
The network.
We instantiate the parser, and then the network definition is basically just a file I/O.
It's the prototext file you're talking about?
Yes.
The Caffe model.
Yep.
But weights are in the Caffe model
Weights
file.
are in the next. So basically, these are you give us two file pointers, one to the weights, one to the prototext.
I think you're basically programmatically create a graph, right?
You can do basically two ways. One, the Caffe specific right now is a streamlined path where you just give us the files and we parse them. Hopefully we'll do this in the future for TensorFlow, but we currently only have it for Caffe. If you don't, for any network, for any framework that you start from that isn't Caffe, you can programmatically do it using the second API. So you can start, that's why I claimed at the beginning, you can start with any one of the training frameworks and get it in TensorRT. You have to have one that's pretty easy, one that might require a little coffee and coding while you just sort of loop over your layers. Okay? Yes?
So for the max workspace, like what's the scope of that exactly? Like what?
That is setting
multiple models running in the same runtime?
That's for one, that is, so for one execution context, there's actually a little bit of complexity. I don't know if I go into here between engine and execution context, but this is setting this base up. This basically saying the algorithms that you use in executing forward pass only inference for this network, those algorithms should be allowed to make the assumption that they'll have at least this much working space to use for optimization. So again, when we're going through our kit of tools, there'll be some algorithms that are really don't use a lot of space and may take a little bit more time. We'll have some other algorithms that may sort of spread out and get comfortable in a larger workspace, and they may run faster. And this is basically putting an upper limit on that. And if you run multiple, you can run in one model, multiple contexts, you would be reserving, because you want to be able to run both at the same time, and use the memory for both of them. If you set this to 1 gig, then that would be saying that when it instantiates an engine and a context to run, it would be setting aside at least 1 gig for the workspace. It might do a little more, but it's never going to do less, because then we might select the wrong kernel.
And that's a multiple of the batch size typically, or?
This would be just a maximum, and then the batch size also affects how much memory we need.
Right. So those are somewhat. I mean,
they're related. They're related. Probably if you had a large batch size, you'd also want to give the algorithms the ability to use a large workspace size.
What's that, like memory size you're giving?
Yeah, both of those are memory sizes. So sorry. This is a memory size. This is a number of separate inputs. Whatever your input is, whether it's audio clips or images or 12 months of stock prices or whatever it is. Right.
And this is batch on just the forward prompt.
Again, this is all forward prompt. This product is hyper focused on, I've already got a trained model, I want to run it fast. So no backward prop at all on this product. Again, we have other tools that do that.
How do you optimize the size for the workspace?
how do you optimize the size for the workspace?
You just run like like a grid and then fine until it crashes, or
you would. I think the user's guide has. I don't remember what the number is. I think it has a recommendation for a starting place for a number, and then you, most people would probably just pick that one. And then if you want to try a larger number and just see if that gives you more performance. So again, choosing a larger number is basically telling TensorRT during your optimization you can use algorithms which are more doing space time trade-offs.
Oh, I see. Okay, so you define by the size the backend chooses the right.
Yes. Yeah. You just set this, and then that gives us a constraint that we work inside.
Is this a wrapper over QDNN? Or is
This does use QDNN, but we have a lot of our own kernels as well. So this has so it's not it has QDNN as a dependency, but I wouldn't describe it as a wrapper over QDNN because we have a bunch of other functions.
Does this have an interface like digits, or it's just C++ code?
This is C++ code, so it doesn't have a GUI.
So in your experience, the batch size selection, does it vary whether you're using image or audio or natural language?
It is very use case dependent. So what we find is that if you are in a case where you're in the latency domain, then then our customers usually find that they'll want to choose a small batch size. If you're in a sort of data at rest, just sort of pipelining through lots of data, then you'll choose a larger batch size. Within that sort of domain, if you're trying to decide between 4 and 8, and you actually mostly are going to have 8 values available, I would encourage you to try the larger one because usually you get better performance. Overall throughput. So you kind of want to go to the highest one that you can comfortably accept. It gives you a latency envelope you can comfortably accept. This is what I would encourage people. Does that make sense?
Yes, kind of.
Okay. And I'll show you the graphs later on that I think make that make more sense. And then executing it. Once you've done that, so the previous 2 slides were the code to get the model in. This is again pseudocode, so I'm glossing over some things. But this is the sequence of code that you use to actually execute. So basically, you come in, you create the execution context, there's a binding to the binding index. That tells you the layer name where I think your outputs are going to come. You'll have to do some malloc, allocate buffers for the data coming in and coming out. You'll create a CUDA stream, and you want to do that if you want to have multiple things going at the same time. And then you'll do your copy data over in queue and copy data back. And then this is a synchronous.
I have a dumb question. Yes. So you have selected batch sizes, right?
Yes.
For image and audio and natural language.
Yep.
Same batch size.
You would set the batch size for
Let's just say hypothetically select same batch size.
Okay.
Which one would have the best performance? Is it dependent on the data heterogeneity of the data also, or is it irrelevant?
For a given neural network, let me go ahead and go to the performance graphs here, and you'll see. For a given neural network, so this particular neural network is ResNet. It's an image network, but we could do the same thing with an audio network. Generally, as you go up into larger batch size, we will show higher throughput. So this is number of images per second. So you can see as you go from 8 to 16, this is the bar for FP32. TensorRT is doing about 800 at 16 and only about 600 or 700 images per second, taking 8 of them at a time. So it's more efficient when it picks up more of them and runs them all through at the same time. So that's a general trend we see. Almost all of the graphs in this representation go up and to the right as we go up to larger batch sizes. They will tend to sort of table off. At some point, you have all the working units in the GPU full most of the time, and so it sort of tables off. But that's why it's not optimal at the low batch size. You may not fill up the GPU. The GPU is kind of its happiest when all of its parallel units are working at the same time. So small batch sizes don't always fill. But you turn that around and look at that in terms of elapsed time to do those 8. This is now latency, milliseconds to execute the whole batch. and now I'm doing it in a log plot. And what you see is that at a given, as you go to a larger batch size, of course, it'll take longer to do all of them, but each one of them happens faster. So that's the trade-off. Does that make sense? And I think I generalized. Now, generalizing between different models and different domains, there's too many variables there for me to do. But within a given model, this will be the kind of curve you'll see. And then the choice is just what's your latency envelope. If it's long, if you don't care that any result happens, particularly, you don't have to look at the result right away. Then go to the largest batch size that'll fit on your GPU, and you'll get the best performance. If you do care, then you'll have some max. You have some ceiling. Like let's say you're doing a speech application, and you know that in 20 milliseconds, you need to have an answer, right? So you're not interested in any part of this plot that's above 20 milliseconds, right? So you can basically cut that plot off, and then you'll see that, and actually these are the graphs for TensorRT, that's for the CPU, that's for other frameworks. You'll see that your batch sizes are maxed out at some point. Does that make sense?
I have a question. So
yep.
Image, how many tensor
For this particular one, we're using the standard image net competition version of this. So it's, I think, 224 pixels by 224 pixels.
224.
That's right. Look it up on the paper. I don't remember what it is. It's some number around there. It's a relatively small image. But those are usually heavily convolutional. So if you have a larger image, you can think of 2x2 tiling of that as being a 4 batch size, or a 4x4 tiling of that as being a 16 batch size. And you'll roughly get the right performance.
Yeah. So I see TensorFlow is just FP32 on the P100. Did you guys try FP16? Does it?
I don't think it fully supports FP16.
Sure.
Yeah. So
it's using CUDNM like the latest and CUDA 8. Yeah, I don't have access.
I would love to see the numbers if it does. That would be a great thing to add to this plot. So the point of this plot, is everyone doing okay for time? I mean, I can kind of cut short maybe even after these slides if you guys are getting tired. Say what?
Don't worry.
Don't worry. Okay, keep going. Okay. The point of this plot that I'm kind of trying to say is the CPU performance hits its maximum pretty quickly in this batch size representation, and that's because it's only do a certain number of parallel things at the same time. It doesn't have that same capacity to do a lot of parallel things. All the rest of the lines are GPU lines. These are the sort of general training frameworks. And of course, they trend upwards. TensorRT takes advantage of some optimizations and allows it to jump up quite a bit. That's all FP32. So this is just sort of software, using panels that are better suited just to do forward pass inference, right? That's where we're getting this bump, and then this bump here comes from the reduced precision. That makes sense? And somebody asked earlier for comparisons with frameworks. This gives your answer.
Is there kind of best source code for this benchmark? I think they are using the same source code for evaluation.
Best source code for this.
I mean, this benchmarking. So pretty much, it's that it's available. I think a lot of run sometimes have some kind of test to compare how this system works.
Yes. So we would encourage you. We encourage you to do
someone that. Maybe, especially some people are designing systems for the power side, server side. I think it would be very good benchmark for performance strength.
Yes. And we've seen AlexNet used as a benchmark, GoogleNet used as a benchmark, ResNet used as a benchmark. Our teams internally look at all of those, and I regularly run on every new hardware and every new software this sort of suite of tests. And we sort of optimize to make sure those perform well. So, and I would encourage other people to do the same. And we encourage you to try this out for yourself. Get TensorRT, take a ResNet model, run it, see if you can reproduce the numbers. You should be able to with our GPUs.
Yeah.
Try your network, see how they behave. We would encourage you to do that. It's good for us all to have good numbers, accurate numbers. Okay, I think I talked about everything I wanted to talk about on both of these. Okay, so the next section of the talk is talking about how we get to this bump, which looks better on this graph. What do we do? What do you need to do to take advantage of that? So why would you use reduced precision? Again, I think you're interested in TensorRT if you care about performance and throughput, latency and throughput. The reduced precision gives you two benefits. One is it allows you to reduce the memory usage. So you can have the same neural network model, the same ability to classify images in less space. GPU memory is not unlimited. People often want to run lots of models, so it's valuable to be able to reduce the size of the model. It also, if you're loading and unloading the images, the models, which you may or may not be doing, if you are, having a smaller model also lowers your memory bandwidth. All right, so there's an advantage to reducing the memory usage. And basically, FP32 is the sort of starting point. This is an actual measured memory used by TensorRT at FP32 and FP16 and at INT8. Same model. It is different hardware, but that shouldn't matter for memory usage. So this one is on P100 for FP16 and P40 for INT8. The reason I did that is because our current hardware, all of the Pascal generation has some kind of reduced precision, but some of our hardware has the FP16 and some of our hardware has the INT8. Right now, in the Pascal generation, none of them have both. So we can only do the appropriate scale values. But the trend here is clear. FP16 doesn't quite drop to half because there's some overhead, there's some stuff that doesn't reduce. And this doesn't quite go down to a quarter, but it's about 3/4. Okay, so memory reduction is one thing, one benefit of using reduced precision. The other one is increased performance. So this is scaled to 1 because I'm comparing across two different hardwares. So FP32 to FP16 on P100 gives you about, and this is at a large batch size, by the way. This measurement is at 128. These multiples would be a little bit less at a smaller batch size because it'd be more overhead, more fixed cost stuff. But at a large batch size, you can get almost twice as fast on the P100 by taking advantage of FP16, and you get almost 3.5 times, 3.2 or something like that, times faster, taking advantage of the INT8 structure.
You already answered the question that I was trying to understand. So memory usage is one, performance is another, and third one is accuracy.
Right, and we'll come back to talking about accuracy. So with FP16, we found, for FP16, we found that it maintains the accuracy very well for the image classification networks that we've measured. There may be networks for which that's not true, and I would love to hear about that and help understand that. But for FP16, we haven't had much of an accuracy loss detected for the ones we've been measuring. For INT8, getting it to work the first time was really challenging, and that's kind of the guts of what I'll talk about in the next few minutes. And actually, there'll be a full talk at our GTC conference that one of my colleagues is going to give on the gory details of how we do this.
So you think accuracy hit is similar for speech and natural language also? That's my conclusion based on what you are showing here.
That's not exactly what I'm saying. So let me talk about the accuracy part, and you'll understand it better. But right now, we've been first able to achieve really good results with convolutional neural networks. We are now looking at the recurrent neural networks. So it's not guaranteed that we'll achieve the same results, but we're still in the process.
This performance is the inference performance, or is it training?
This is inference.
Okay. Does training get worse with reduced precision?
So we actually, that's a really good question. So I think right now, our experience has been that you want to do training in FP32, maybe FP16. Training with INT8 seems to not work that well. There are some experiments where you do the forward prop during training in INT8, and then you do the back prop in FP32. That maybe works a little bit better. But our kind of model with TensorRT, which I think I kind of highlighted, well, I guess I didn't highlight too much, is that we sort of expect, because we're trying to like do this with an eye towards production. So people want to actually use this today, not sort of research. So we're assuming they start with FP32, they do the training with FP32 because they know that works, they trust that. We're going to take that neural network and we're going to do the reduced precision as part of an optimization. So there's more, I think, right now, I think of reduced precision training as more of a research area. There may be something there, I don't know that it's proven. This is kind of known to work. And this is the sort of thing that we've just kind of gotten to work, and why I came to talk to you guys. And that allows you to take advantage of the benefits I was showing in performance without having to change the way you do your training. That's our premise, our promise. Not making sense? Hopefully I'm not ranting too much up here. Nope. Okay, so the FP16 actually doesn't seem to be too much of a challenge. What I'm going to talk about is how we do the INT8 and what some of the challenges are. INT8 is challenging mostly because you lose the ability to express a fraction, right? You can go to minus 128 to 127, and the smallest weight or activation you can express is 1, right? There's no half. That's what it means to be an integer, right? So there's a lot less expressiveness here. You can think of sort of dynamic range, or the subtle features of your neural network are kind of, there's a risk that it can be really attenuated, right? So the things that your layer to layers might trigger off of might not be there if we do a bad job of transforming the neural network. Is this like turning the lights off at the end of a talk and getting me to shut up? I'll take the hint if you want. Okay. So we have to be smart about how we do the quantization. If we just do it kind of naively, what we found was the results sucked. So we have to be clever about how we do this. So with weights, we actually were able to, for the networks that we've seen, we were able to just take whatever the max and the minimum values were and linearly quantize them, and that seems to work just fine. We do a symmetric one, by the way, so symmetric linear quantization. The hard one is the activations. The challenge here is that we don't know what they are just from looking at your model file. That's what it really boils down to, right? We can look at the input data that you give us from your training. We can say for any given layer what the largest and the smallest values are, and we can quantize based on that. With the activations, how do we pick that? So those get generated dynamically when you run, right? And it's very nonlinear. So we can't just kind of estimate, I think it'll be around, like you have to actually run the neural network. So the challenge was, how do we develop an algorithm that we can give you a reasonable process that allows us to find a scaling factor. So we're going to take your FP32 values, we're going to look at them, we're going to say for this tensor, there is a multiplying number that goes between the INT8 representation and the FP32 representation. We're going to set that for each one of the activation tensors coming out of your network. So the way we do that is, this is a slight modification of our previous chart. Again, FP32 coming in, INT8 optimizations. We ask you to also bring us a calibration data set. No, it's not a training data set. All we're going to do is calibrate those scale factors. But we need to see some real data.
What's the difference between a training data set and a convolutional data set?
Well, so your training data set is probably large. Everybody I've talked to who does neural networks, one of the things that they know is it only works if I have gobs of data, right? That's why the big guys are able to do so much with, they have all our information, right? It's huge amount of data. We don't need to see all of that. We just need to see a representative subsample. What we found is that like a couple thousand images, like if you're doing images, usually you're doing hundreds of thousands, maybe a million images that you're training off of, right? Give us a couple thousand for the optimization, for the calibration. What we're going to do is we're going to push those through the network. We're going to look at how those activate the subsequent layers. We want to see the distribution of activations in those subsequent layers when they're working with real data, the data that the network is trained to look at. Because again, we can't work out from first principles what the possible activations are. We need to look at some actual data. But again, we're not going to retrain. We're just setting that value, the multiplying factor between our 8-bit quantization and your 32-bit actual values. But the math has to represent. You want to find a scaling factor that fits best to that. Yep.
How did you choose it? A calibration data set?
We encourage you to just sample out of your overall data, and then if you're going and putting this in something that's going to maybe whack me in the head someday, please test it. Make sure it's getting a good result. If not, go back and look and see if maybe you missed an important corner case in the subsetting. You know, basically, if you think of an image classification network, in order to train, you have to get a huge variety, like hundreds of instances of cats, right, and dogs, and whatever. We only need to see a couple of them, but we probably should see some that are well lit, some that are dark, some that are on a green background, some that are in rooms, you know, so that the later feature layers that are going to activate, so that we're activating all those in about, you know, in the kind of range that they usually activate. Does that make sense? So it should be sampled throughout your whole distribution. You shouldn't just pick, you know, only the red cars, right? Because then there will be whole parts of the network that won't light up the way they usually do, and we'll think they never light up. And so we'll pick a calibration factor that is low, maybe too low, and then you'll truncate, and you won't do a good job. Does that make sense?
So if I choose, like, for each of my features, I pick the records with the max and the min, and I just give them good calculations.
You can do that, yeah. We found that you can just sort of sample, as long as we pick a large enough sample. We actually tested it with like 1,000 and 2,000 and 3,000 and 4,000. We found that we got to a couple thousand, we reached a good level.
So why I'm asking this is because it's like, of course, it's before you generate the plan, but you are taking cycles, right, for your computations.
Yes, we are. Yeah.
So so if the smaller the calibration set, the faster.
Yeah. I mean, but though this is right, when you're doing training, you're probably using a GPU to go over 500,000 images or more, lots of times. But you have lots of training epics, right? That takes weeks or whatever. This is going through a few thousand images once. You only have to look at them once. Right. We just have to do forward prop. We don't have to do back prop. So this actually doesn't take that long. So I said it was like a 30 seconds before. If you're not doing the optimization, it's this. It's a few minutes, maybe 10, 15 minutes. This is not super long. So I wouldn't spend a long time figuring out an optimal way to choose the calibration images. I would just choose a reasonable number of calibrations. Of course, I test it, make sure it didn't screw up. And if it does screw up, maybe go back and make sure I haven't missed a big category of images. But I wouldn't, see what I'm saying? Like it runs fast enough, but I wouldn't spend a long time trying to optimize.
You said not try to micromanage this space. Yes.
If you're worried, you could run your whole data set, actually. So, okay. We're trying to say you don't have. We don't think, based on our observations, that you have to run your whole data set. You could. But, was there a hand in the back? Okay. I'm trying to be good about getting questions. Okay, so the API for doing this, basically just you tell us that you want to use INT8, and then there's a calibrator object that has the batch, and you actually just implement a get batch, which we call to pull in the data. It's pretty simple. Okay, so you've been asking for this slide for the entire presentation. This shows the results that we got. So again, right now, so far, research has been mostly around the ImageNet networks, because just we understand those best. The team right now, hopefully they're home and not working. If they're working, they're working on the recurrent neural network stuff. So we're trying to replicate these kind of results. We are finding it's a little harder, but you know, we're working on it. Okay, so for AlexNet, what we're looking at here is the top one accuracy. Hopefully you guys are familiar with that terminology. That means did it get the right label in the exact top category, the highest weight, highest probability. Obviously AlexNet was really awesome when it came out, but it's not all that high a number. But the main thing is that the number doesn't change that much, right? We wouldn't expect our INT8 to make it better. It's going to maybe lose a little bit. what we want to do is lose as little as possible, right? Ideal would be 0. Ideal would be 0 here. CoolNet, VGGNet, basically they all get, you know, as they, in this order, they get more accurate in their FP32, and they get more accurate in the top one, and then the difference is shown here. This is with INT8 calibration without anybody doing any retraining. So this is you guys take your neural network, you bring it to us, you bring like we said, a couple thousand calibration images. You basically just set a flag, you run it through, you feed in a couple of thousand images, and you lose a little bit, we hope, but you gain this. And that's up to you. You don't have to use our INT8 stuff. If this loss is a big deal to you, and you're willing to give up that, then you just use FP32. But if you want this, and you're willing to give that up, then we think it's an easy way to get it. Does that make sense? Yes.
Yeah. So if I understood right, so if for each, let's say at each pixel level, you're moving from 32 FP32
yes.
to INT8. So
INT8 activations and weights.
Yes. So you're basically losing the depth of information at the pixel level and gaining performance.
Yes.
Given that it solves the problem close enough.
Yes.
But let's say your problem has to deal with color shades and variations, then that might not work that
right. Yeah, I am not claiming that this will work for absolutely every neural network. I'm totally willing to, I'd be really, I think there's a high probability there exist neural networks that are sensitive enough to the fine details that our INT8 calibration would lose too much on the accuracy.
So somehow, if you say, going back to the batch sizes, somehow, if you say, I don't know technically, mathematically, if it's possible, you break down the entire pixel information itself into multiple records and use the other batches, something like that sort.
I mean, there might be some way of doing that. Now, if you took the pixel information and you put it in 4,
yeah. Then
you'd be making your batch size 4 times larger, and we're generally giving a first game that's a little bit less than 4, so you're probably better off just staying in FP32. But you know, maybe there's some middle ground in there.
No, it has to go back to the training phase. The thing has to come from the training phase itself. Yeah.
And that would be a big change to your train. Yeah, you would have to actually explicitly train your model to do that. Take advantage of that. Okay. Anybody have any questions? I mean, this is a dense chart. Does anybody have any questions on it? I mean, there's a lot of things you could ask about it. Not that many numbers. But, okay. Actually, if you guys just want to understand about TensorRT, I can stop here because I know I've gone kind of long. The last stuff is about REST services. So you guys want to hear about that, or? Yes. You do. Oh, okay. Awesome. So GPU REST Engine is a thing we put together at Nvidia. For a while we were calling it a product, but you know, it's something we put up on GitHub. So it's an open source thing that you can look at. You can run with it. You can change it. You can do all kinds of things with it. Its purpose in life is to help you understand how you can create a REST service out of any old GPU function. And basically the problem that it solves is GPUs are sort of limited, scarce resources, and we wanted to basically show you how you could, with a little bit of code, sort of efficiently use those GPU resources in a batch environment, in a REST environment. Does that make sense? Let's see. Yeah, the main thing here is it's just really easy to start with a CUDA kernel or a function which uses CUDA and create a microservice out of it with GPU REST Engine. So our idea here is that you have some somewhere service-oriented architecture for your whatever your service is, or whatever. And kind of in the drawing here, this is a REST API to a thing, and then it's making other calls to other REST APIs. And the idea is most of those will start out blue. If you want to GPU accelerate some of them selectively, you can go in and just take that REST service and GPU accelerate it with GRE. So, and we happen to have a product called ICE, which is kind of like this, which does image resizing as a REST service. Okay, so I don't think I have the code for this here, but if you look at GRE on GitHub, it will give you an example, and the Hello World example is this Hello World microservice, which runs a kernel which basically does nothing, but it actually runs on the GPU. And the idea is, well, how do when I'm getting a random number of requests coming in on my REST API, right? You've got clients, you have a bunch of clients making requests to the REST API. How do I make sure they don't all try and run on the GPU at the same time and sort of stomp them? So that's the challenge that we're trying to do. So this is the layering that you have. You have your HTTP layer. In GRE, it's written in Go, which we used because it was super simple. The code for the Go thing is like 15 lines. That runs on the host CPU in Go. That's the HTTP layer. It's going to call the app layer. So this is where you put your whatever your business logic is. That's, in this particular case, it's created in C++. Again, it runs on the host CPU. It's going to call an object. It's going to instantiate an object called a scoped context. This does our resource management. This instantiation will only happen if there's an available scoped context. So here's the idea of this. Basically, the contexts create a pool. We set up that pool with a limited number of contexts. We want to have at least 2 contexts per GPU. Could do maybe 4, but you probably don't want to have a zillion. And then when those contexts are available, they'll get assigned in whatever order the requests come in. Any request that comes in when all the contexts are occupied will pause, because that object constructor won't be able to execute until there's a free context in the pool. So basically, you don't have to do much other than just instantiate a scope context at the beginning of any logic that might then subsequently use CUDA. And this mechanism takes care of making sure you don't run too many of them. They won't stop running. Does that make sense? Okay. I mean, I'm going quickly through something that is maybe a little bit complicated. Once you have that, then this function continues to execute. Then you can do your host CPU side CUDA code, which then calls into the device code, which runs on the GPU. Right. So you do all your data movement here, which can be, in this particular example, because we wanted to make everything explicit, it's explicit if it's explicit CUDA. In a later example here, I'll show this could just be a function which happens to use CUDA, right? And again, you call that function after you've gotten the scope context in your business logic. Does that make sense? And here's the code for this. This is an example of what you could do with TensorRT. This code actually is drawn from when we put this up on GitHub, which was about a year ago before we had TensorRT. So this actually uses a cafe model, but you could totally do TensorRT here instead. I actually thought about just changing the API calls, but I didn't want to give you guys wrong information. So this actually compiles and works, whereas what I would have hacked together wouldn't necessarily have done that. I'm going to probably try and do this presentation again at GTC and have done the math, the homework to put up the TensorRT version. But the main idea here is you just write a simple bit of code where you instantiate a context object. Oh, sorry, no, this is initializing things. Sorry, we're creating the cafe context. We're creating the pool, and we're setting the pool to have 2 devices per device. And then here is where we use this, right? So in your code that actually runs in the business logic that actually executes the thing you want to do, to generate the response to the REST request, you just instantiate a scope context object that will only return if there's a context object available. If not, it will pause, which allows the other things to finish, and then it'll execute. And then from here on, you just assume you own the GPU, you call your other calls, and you're good to go. And when you end this function, this goes out of scope, the context is returned to the pool, and then some other request can proceed.
Can you run cafe as well as some other context? Because this looks like the pool is tied to cafe context.
That's just typed. It's just typed so that you could actually have a single service that had a certain number of contexts for cafe and a certain number of contexts for something else, and it's just typed. But there's nothing special about it being cafe. I could have gone through it. Again, I thought about doing this. Just change those to the TensorRT function calls and a TensorRT name. the same code would. This is all sort of business logic that protects the GPUs so they don't get oversubscribed in a REST service. It wouldn't care what it was actually running. And actually, if you go to the GitHub, our sort of open source thing for GRE has like 3 or 4 examples that do different things. So we sort of we show you this template, and then we show you how you can use it in 2 or 3 different ways. Make sense? I think I was always going to show for code. Thank you for putting up with code and code that actually had mallocs, and a few people left. I assume they were allergic to C++, but most of you hung through. So what I hopefully I convinced you of is inference is important, and it's going to power an increasing number of important features and things that we're all building and doing. That latency is important for responsive services, and throughput's also important. And the trade-off there depends on your use case. GPUs can deliver both. And in particular, at a given latency, we can deliver a lot of throughput. Reduced precision gives you an extra boost in doing that. Hopefully you guys all saw those graphs. And we have a template. The GRE is a template you can use to create accelerated microservices. So it shouldn't be scary how you can. To learn more, if I haven't completely sated your curiosity, there are a couple of resources I want to point you to. We have a GPU Technology Conference, GTC we call it internally, which is coming up this next month. It's right here in San Jose, just down the street. There are 2 talks. This one will likely be boring to you because now that you've sat through this will be a souped up version of what I just went through. This, however, is the gory details on how we're doing the INT8 calibration, including some stuff that I didn't want to talk about because I want to leave it for him. So if you'd like to come hear Simone talk, that would be awesome. We also have 9 Spark and 17 TensorFlow talks on the agenda. So. Contribute and help him out. There's 2 of them that are really good on TensorRT. And they had long titles. We seem to go for long titles. So I just give you the first few words. So search for parallel for all and those words there, and you'll get to the blog post. They're both good. And there will be more in the future. This is our Deep Learning Institute, which is an online training series. And also has some in-person versions. So sign up or check that out. And I guess you're also giving some training on some of this stuff. So check out the training resources that are available. And then Dusty is one of our great solution architects at Nvidia, and he has put some stuff up on GitHub himself. So he went and ran with some of the stuff that was in this blog and went ahead and put it up on GitHub. So I've heard lots of customers tell me this was the most helpful resource around for TensorRT, so I put the URL up there. So that is all I have. Thank you.
Yeah, by the way, GTC is badass. It's like, yes, I went last year. There's like 9 tracks or something, and it's not just video games and stuff anymore, right? There's all kinds of research, and it's hardcore. Yeah, it's
Automotive, robotics, cloud, HPC, and video games.
And video games.
What's not to learn? Oh, and VR.
Yeah. And yeah, I'm speaking on both Spark and TensorFlow. So
you're responsible.
They double counted.
Awesome. Cool.
We're going to share the slides on the Meetup.
Yeah. Do we have a way to share the slides afterwards on the Meetup?
Yeah, of course. If you can send them, just send them to me.
More than happy.
Okay. Oh yeah.
Yeah. No, the volunteering.